I am going to talk about climate change. One of the reasons is it is the greatest challenge as human beings that we face today. And I'm pretty sure about that now because the Pope agrees with me, as we saw last week. So it's only right, I think, that it is actually forming a good part of science school curricula around the world. It's important that we do that. Education, education, education is what's needed for the future. So, what is climate change, global warming and the greenhouse effect? And I'm going to take from the point of view of a very good analogy, which is the greenhouse effect of what we're living in at the moment. And I will talk a little bit about the history and events that we are linking these days to climate change, but we are the most important part of all of this. The anthropogenic era that we're in means that we are crucially affecting our environment. So I'm going to begin about 2.5 million years ago at the start of an ice age, which really means a period in which we have glacial and interglacial periods, that's cooling and warming. And I'm going to move up to about 12,000 years ago. And the question might be, well, why are you going up to there? And the reason is because it's when we as human beings first began to really do things to our environment. We became civilization, we became societies because we worked together, and agriculture was the very first process that we got together with, and then that ice age began to change a bit. And so now we're in an era of warming, and it's been warming ever since. And perhaps the heart of the message from this lecture will be that we are warming at a very accelerated rate because of our activities, mainly to do with combustion. I'll be talking about this thing that I call the Anthropocene later. The anthro bit, of course, comes from the Greek meaning human beings, and this could be defined as a start of the Anthropocene. I have another personal favourite, and I'll talk about that later. The first issue that you have to get over, I think, to students or to anybody, is what the difference is between weather, perhaps the most important topic of conversation in Ireland, and climate. Weather is short term. It describes temperature, pressure, wind speeds, wind directions at any one point, at any one time. The difference between that and climate is that climate is long term. It looks at trends, it looks at averages over perhaps periods of 30 years or thousands of years, certainly hundreds of years. So we have a difference between that very short-termism that we call weather and the much more longer-term issues of the things that we know affect us that we call climate. Now, the question often comes is, are we experiencing climate change at the moment? I was interviewed on radio only in autumn of last year. I can't remember, it was some local station that got completely the wrong end of the stick with me, but that doesn't matter because they were worried. It had impacted them, the fact that it was warm and it carried on being warm almost into November. Now the farmers were very happy, but people were saying, is this the start of climate change? The answer has to be maybe it is, maybe it isn't. We'll see over many, many years if, for example, we get these sort of Indian summers every year for 20, 30 years, and maybe if they go into November and December, we might begin to think we're getting differing weather events that are coming together as a trend for changing climate. And if you notice there that this Halloween, it was about 9 degrees centigrade above normal last year in Phoenix Park. Let's contrast that with the real Indian summer, when over 2,000 people died because of this month-long heat wave. And there's another one going on in Pakistan at this very moment. And temperatures there, of course, it knocked Phoenix Park into cocked hats, from going from about 19 centigrade, and was more like 50 centigrade there. But if you want to look at it from another point of view, because people would say, is this climate change again? It is only about 3 degrees possibly above normal for that month or two. So once again, this may be climate change, but we're not certain. What we are certain of is that the climate is changing. If you want to look and direct your eyes to this area where we have temperature here that we're going above some sort of baseline of say about 50, 100 years ago, we'll see that we're getting a lot warmer in this red period, and the red period is between 1990 and about now. Whereas if we look at this whole trend between now and many years ago in the 1850s, we'll see that the blue end, which is what is there, is when that temperature anomaly was not as great. So we can see by looking at climate that we do have an issue that is happening. So there is change. We just don't know from day to day whether it's absolutely to do with that these increases in temperature are affecting our planet. And there are problems that begin here because the Earth is not a laboratory experiment. It's a very complicated set of physical and chemical and biological phenomena, and it's very difficult to predict if you do something. Perhaps if we want to solve climate change, we might want to do some geoengineering of our atmosphere, and the man who won a Nobel Prize for the chlorofluorocarbon ozone issue, Paul Crutzen, that John just mentioned, was one who said perhaps we should put sulfuric acid droplets up into the stratosphere in order to cause reflectivity. We'll come to this point as why that might be a potential goer fairly soon. But when you do something like that, and the CFC problem was exactly like that, people were replacing refrigerants, ammonia and sulfur dioxide, because locally, if they broke down, then somebody might get gassed by the effluent. And that's why these very inert and but perfectly formed for the job of refrigeration, chlorofluorocarbons were invented. But nobody suspected that because they were inert, they would float up. So our environment is like a beanbag. You may push something in and something goes out at some point that you don't really understand. So we have to be careful. Climate, though, is linked to our environment. We can see it in all different ways, but the most important ways are our air, our water, and our land, and perhaps most important, us, life. So these climate change issues that I've got listed here manifest themselves in a number of ways, and we hope they won't manifest themselves to a larger extent over the coming years. In terms of food production, this is going to be one of the biggest issues in 20 years' time, of having food security, really, of people being able to produce enough food to live. Drought, of course, will be connected to this. Everybody has a right to clean water, as much as they have for clean air. And we've got to make sure that just because of our activities now, that some future generation doesn't get a problem by not being able to drink clean water. The ones that we see every day, I suppose, to do with climate change, the polar ice cap melting and save the polar bears. And the final one that I think does impact most on us is because it is to do with that weather issue, is these extreme weather events, these typhoons, Katrina, flooding, heat waves, unusual autumn weather for Ireland. So these human security problems may arise because of these extreme events. So they impact on us. It all really starts with the science, in my view. That's why it's so important, I think, that it's part of the school curricula. So we do have to make some understanding of what's going on in order to be able to show that politicians and policymakers have a firm basis for doing things that might prove to be unpopular, including things like raising taxes. John has already spoken a bit about the atmosphere, so I don't really have to go into the whole issue of troposphere, stratosphere, etc., etc. And he's also gone into the idea of the atmosphere, importantly, acting as a suntan filter to us. What my issue will be over the next 10 minutes, 15 minutes or so, is the way of thinking of that atmosphere also as being a shawl, a woolen shawl. So it's a woolly that keeps us warm, and that's what we need on planet Earth to at least be kept in a temperate climate. But that woolen shawl obviously has holes in it, so that when we're producing heat with some sort of baseline warmth that keeps us well and alive, that there's a reason for it not getting over hot is because the heat can escape the holes. So I think this is an analogy that I'll be using for the science part in a moment. The second thing I think perhaps that you should know about the atmosphere is that it's a fluid and pollutants move around. So it's not just that we throw up some sulfur dioxide here today and it doesn't get anywhere else, even 100 kilometers away. It does. It's sometimes, if you want an analogy here, then it's perhaps likened to an ocean above our heads. It can be likened to a sewer as well, because there are some pathways that push things around, and the jet stream is one of them. So that, I think, is something to put over to students, that it's not just a static thing that you're throwing things up into the air, that it's almost living. So 1 to 2 years, you put up a pollutant and it can get to another hemisphere, the other hemisphere. So in the end, we get full mixing of whatever we put into the atmosphere, as long as there'll be reactions as well and physical processes that rain some of these things out. But over time, we will get everything everywhere. And the third issue that I'll sort of describe the atmosphere as a chemical reactor, and really talk about how the chemistry and its composition affect climate change, global warming, whatever you want to call it. Now, every school student should know the first part on the numbers here of the table: 78% nitrogen, 21% of oxygen. They should know as well that there are other bits and pieces that don't really contribute that much. Perhaps the most important being the carbon dioxide, and in 2005, what this table shows you is that there's 0.035%, and that translates in John's terms to 350 parts per million of carbon dioxide in the atmosphere in 2005. Now, one issue that I think is also useful to appreciate is that John was talking about things at the parts per trillion level. And I think that's the point, is that the 78% of nitrogen really hasn't got a great deal of effect on us. But parts per trillion of highly reactive chemicals can have severe effects on our environment. Ozone was the example that we had just now. So 2005, 350 parts per million. In May 2015, that had gone up to 403 parts per million, and it's by volume, as John had said as well. Now, how these are connected to climate change is that most of the species I've got in the table allow UV light through, and visible light as well, to get to the surface. And what happens to high energy radiation when it hits the surface or us, or animals, plants, whatever, is that it becomes degraded. And it becomes degraded down to a lower form of energy, which is heat or infrared radiation, as was shown on a table in the last lecture. And those things try and bounce upwards. Now, of the group of chemicals in the table, carbon dioxide is the only one that can really trap that heat. And that's really why the greenhouse analogy is so good, is because that's exactly, as you know, I'm sure, what happens in a greenhouse. One of the species that wasn't in that table, but is of key importance, and it's certainly of key importance to the greenhouse effect, and I'm going to distinguish what I would call the baseline greenhouse effect, the thing that keeps us alive and warm, from an enhanced greenhouse effect later, is that a very key component of the greenhouse effect is water vapor. Now you can see on the little diagram there that water cycles throughout, so it's a bit different from the other species in that it ends up in the air, it might be in the land, it might be in the oceans. When planet Earth began and we began to thrive, it was a difference in the atmosphere itself at the very earliest stage of creation. And for some time, there would have been a temperature on the surface of that was very low. I mean, it may have been -18 or very much lower. When, though, a small amount of carbon dioxide began to go into the atmosphere, that allowed the temperature to move above 0 centigrade, which then allowed the water vapor to begin to go into the atmosphere. And there was a feedback then, because the water vapor, like carbon dioxide, can take up infrared radiation. So we needed those two ingredients really to come to the position that we would call, I guess, a temperate climate for us to be able to live. And this, of course, is the thing I'm sure that you put into all of your school lectures, where you have the idea of the sun, its rays not being stopped by the glass, going in to do a bit of photosynthesis and bouncing and being degraded, but then being trapped by the glass itself, the silicates, because of the material that it's made of. And that's exactly the same as it is for the atmosphere, where it goes through the atmosphere, all of those ingredients that there are, gets degraded, and then species, molecules, are able, like carbon dioxide and water vapor, are able to trap that heat in. Now, a bit more, I suppose, scientifically for you to take away is what this baseline greenhouse effect is, and that is with the carbon dioxide being excited, if you like, put into resonance by absorbing infrared radiation, and it's then trapped in the atmosphere, as I said. So this is a scientific picture of what's going on. And a message, and I'm repeating this, I think this is the third time now, is that Earth does have a baseline greenhouse effect. The greenhouse effect is good, okay? But it's when we begin to augment that greenhouse effect because of our activities, do problems begin to arise. And here, I think, if I were to pick after yesterday's lecture, the key slide is this, to take away and digest, is that the enhanced greenhouse effect is because of things that we do. That blanket, or that shawl, as I put on earlier on, with holes in, does allow, in the natural state, some of the heat to escape, so we don't get overwarm. But if you begin to fill those holes in the blanket, if you begin to make that blanket a bit thicker, then you begin to accelerate the warming of those of the atmosphere itself, and those that live beneath it begin to suffer. And a variety of ingredients can fill those holes. If I look at what contributes to the greenhouse effect, yes, here, notice that water vapor is not here. I'm talking about the enhanced greenhouse effect, okay? So this is the effect that adds to the problem. 56% is due to carbon dioxide, 18% to methane, 13% to the CFCs, ozone is about 7%, and nitrous oxide is about 6%. And the augmentation of our problems that we have, it becomes where the greenhouse effect is no longer good, it's bad, because it may lead to the climate change effects that I've said earlier on. I say may now, but I know what I really mean, and it will cause issues. Now we quantify these things. John was talking about the chlorofluorocarbons. We quantify how much ozone is being destroyed by relation to those very important chlorofluorocarbons, and so we pick CFC 11 as being 1, and then all the other chlorofluorocarbons as being a factor larger. The GWP, that's the global warming potential, takes carbon dioxide as the baseline. And as an example, I put nitrous oxide. There are other numbers you can look up for yourself, but nitrous oxide is about 250 to 300 times more effective in the greenhouse effect. That's on an error bar, by the way, 250 to 300. Notice that you can calculate these potentials over differing periods of time, 20 years, 50 years, or 100 years. So that's what that range really means. Yesterday, I got a resounding silence from my audience about this important slide, and it's important because these are the infrared spectra of a number of those enhanced greenhouse species where we've got carbon dioxide and it takes out heat here and here. But notice that the importance is taking out, filling in some of those other holes, ozone here, nitrous oxide here, methane here, even carbon monoxide, and of course our parent water vapor, needed obviously to be measured in the very first place. The infrared spectra needed to be measured. And believe it or not, it was about 1860. I don't know if I know there is nobody from Declan's reading who comes from this county. Who did that, and what county did it come from? I'll give you 3 seconds. 3, 2, 1. Nobody. Yes? Who? Sorry, I didn't hear. I thought you said Cork there, but I'm an old man now. Who did that? Well, it was John Tyndall from County Carlow. He was a very important and effective scientist, but possibly one of the most important in the world. If you think of the whole contribution that he's made to scattering and the environment, knowing that he measured really the first pollution spectra that were in London, as I showed on the last slide, shows his contribution. And one of the things he did was, by looking at those spectra, he was able to calculate the ozone, because of its resonance as being quite different from the water and carbon dioxide, could absorb about 80% of the sun's radiated heat. Something else that was predicted a long while ago about the science involved with climate change and global warming was by Arrhenius. Now, this quotation mixes together his 2 important other contributions that you may well know about in chemistry, but may not have known about this one, is that it joins together acids and temperatures in some way with his definition, and also the kinetic idea of rate coefficients. Notice rate coefficients, not rate constants, in chemical, do vary as a function of temperature. But he wasn't bad here. He's saying that carbon dioxide going up from a value to a doubled value would increase the temperature from about 5 to 6 degrees. Now, maybe billions of dollars later, 120 years or so of computer modeling time, really comes to the conclusion that what he's saying there is almost correct. It's probably about 4 or 5 degrees rather than 5 or 6 degrees, but nonetheless, I think it does show that don't ever forget science that may have been done 150 years ago. Even though it was done then, it still holds up very often. We may be able to do things better with more sophisticated instrumentation, but it doesn't mean that there is anything really different underneath. I talked about the Anthropocene earlier on. My view of the Anthropocene beginning is at the Industrial Revolution, because that's really when something that has affected our planet began, and that was to increase that baseline for carbon dioxide, leading to the augmented or accelerated, enhanced greenhouse effect. And you can see on this diagram that at the earliest times there that we have, which is pre-industrial revolution really, it comes about there, is of the order of about 280 parts per million. That industrial revolution kicks in around about 850, and this is where we begin that increase. And the worrying thing that I've said, and we see that this goes up even further if we were to extend this graph, really begins to accelerate upwards at this time you can probably even tell by looking back at the literature that we've got here our maximum is about 345 parts per million of carbon dioxide. So my bet is that's at least 10 years. We might see it 10 years ago. We might see that in a minute. But that is the thing that began to change how we really, agriculture had, of course, but this really has in a detrimental way. Agriculture was a good thing. Now, I read this morning that numbers numb and stories sell, but I need to put some numbers here, quite honestly, and it's going to be that bottom table that we come to in a minute that's important. But for now, just look at this data is from a long-term experiment carried out in Hawaii to measure the amount of carbon dioxide there in the atmosphere. And we see exactly the trend that I've been saying. It's been going up, and we can see here that the most recent data is over 400 parts per million. And as well, you should notice on a smaller time scale, you clearly get this diurnal variation, and that of course is to do with photosynthesis as being the important issue to do with carbon dioxide release. But let's go to that table, because it is important. Only two numbers may even need to be important. If you look in the 1960s, our carbon dioxide was going up by about less than 1 parts per million per year. And if you look now, it's going up at well over 2 parts per million per year. So you see that rapid increase of numbers where, particularly in the last 10 or 15 years, we really have begun to perhaps get on a train that we can't stop. Now, in your curriculum and in most places, you'll see that the issue of climate change and global warming has a greenhouse gas focus, and that's where it was until the 1990s. And I've talked about a few of these things already to do with climate, what it was like before 1750, what the greenhouse effect is, and there was this natural phenomenon and there's the man-made phenomenon. Then we got the Industrial Revolution. So all of this sort of weird tree diagram is one that I've discussed and you can look at later, because as you know, we do have these on our crack.ucc.ie website for you to look at. But the greenhouse gas focus, and remember as well, please, water is not a gas. So when you get questions asked about what greenhouse gas is water, or how does water vapor increase the greenhouse gases. It is sort of annoying, I think, and examiners ought to change their understanding of what's going on. But today we have a new kid in town that we know now affects climate change and global warming as well. And it's the effect of aerosols. Aerosols are small particles, small droplets. We know droplets are in the atmosphere, obviously. Rain, at the very least. We know that we throw up dust. So these are particulate matter that we would say is heterogeneous as opposed to homogeneous, which is when you just think of the atmosphere as being a pure gaseous fluid. There's a number of ways that we can get these aerosols in. There's natural, of course, and volcanoes can throw sulfates up themselves, and we'll see that this is important, specifically different and important from, say, industrial emissions that throwing up organic carbon or soot and biomass burning, because those particles will have differing physical effects on the atmosphere. And this is why it's so difficult for scientists to come out and say, we know exactly what's going to happen. It's because we've got a lot of uncertainty, particularly with the aerosols. Not really much at all with the gases now. It's an easy problem in comparison. But we at least do appreciate the fuller puzzle these days. And you've heard of the greenhouse effect. I know probably haven't heard of the White House effect before today. What this is when the anthropogenic aerosol releases that we have, so it's not really necessarily to do with the volcanic emissions, that throw up aerosols into the atmosphere and float up, and they have two differing features. The sulfate aerosols that we talked about are reflective. And so they lead to a cooling effect because the sun gets reflected out before it gets in. On the other hand, the sooty particles, the black carbon, can absorb heat. So if you throw those up, then they actually augment the greenhouse gas effect itself. So this is the point of the story that we're at the moment. We don't fully know this balance between cooling and warming that there is. Naturally, we do. I have my Game of Thrones sort of statement here that winter is coming. It's been several times over the millennia that we have noticed that when a large volcanic eruption happens, that we get some sort of temperature change, a cooling, a mini ice age or whatever. And I've picked this one just as an example, this huge volcanic eruption. It's one of the biggest ever recorded in Mount Tambora in Indonesia, because it's the 200th anniversary this year of the 1815 explosion. And you can see that by spring of 1816, the temperature changes throughout the whole of Europe, but particularly here, and probably there weren't measurements in Ireland exactly, is that -3 from normal was important. That's because the sulfate aerosol had gone up and began to cool. And because the atmosphere is a fluid, those sulfate aerosols had been transferred throughout the planet. This is an emotive slide, and I'll try to bring it back in the slide after with real data. We're almost at a point where it's too late to do anything. In 2009, there was a Copenhagen summit. Wasn't quite as successful as the Montreal Protocol for the CFCs, which stated that after much deliberation, it had been decided, worked out by scientists, that if we kept the global warming to about 2 degrees centigrade plus from where we had been, is that probably the world could cope. The ideas that were put forward in order to get to that point and not exceed that point at Copenhagen were debated, and they're mainly to do with the burning or banning the burning of fossil fuels, but the USA and China disagreed. So we're now in a position that we're 6 years behind that time scale, and fortunately there's another UN climate conference in December of 2015, and you should read the newspapers, I think, after that, because I think that is the crucial one, because everyone really is saying now that this is the one. If we can't do things by about 2020, there's going to be a real highly accelerated global warming climate change effect, and that we're close to it, and if we go beyond it, we may have 4 or 6 degrees extra. And if we get that, then without a doubt the climate will change, so that we get floods, droughts, wildfires, storms like Katrina that we had, and heat waves, all of these things I've talked about already. Who knows what might happen by 2050 if we don't do anything now. That was the emotion. Here are the numbers. This is a slide from the Department for Environment, Food and Rural Affairs in the UK, and it was done by their chief scientist called Bob Watson about 3 or 4 years ago for the Copenhagen and post-Copenhagen debate. And they give 3 estimates really, low, medium and large estimates for putting carbon dioxide into the atmosphere. And you can see that already we've exceeded what was part of their low estimate for increasing carbon dioxide. And what they said there was, well, that's the one that's going to give us the 2 degree centigrade warming. What is the belief now is, because nothing is being really done, is that the medium estimate is going to be the one that we're aiming towards, which let's say between 450 and 550, which may lead to 4 degrees centigrade rise. And we have to think about what the implications of that are. And of course it goes really crazy. If we got the 650 to 750, that probably does mean the end of life on the planet. So here's what it means. I pay my due deference to the encyclical here, and these impacts that I've mentioned, up 2 degrees centigrade, which seems to be almost certain now. Can't do much about that. Just means these things about the water supply, polar bears, Greenland, environmental refugees are going up towards 3 degrees centigrade, and food shortages, all of the things I've talked about already. But if we were to go up to the 4 degrees centigrade that many scientists, authoritative scientists now, are saying, then there'll be millions of environmental refugees, because lots of land will go underwater. I mean, a third of Bangladesh is predicted to go underwater. The permafrost will melt, and some of the gases underneath it will release, and that will cause a feedback, because those gases are very often greenhouse that can get into the atmosphere and cause even more warming. And I don't really even want to look at the global warming that's even worse than that. Now, just so I know you've had about an hour and 20 minutes of lecturing, the sort of thing that you probably would never subject your students to. Do this test, please. Well, actually, you don't have to do all the questions. I just want you to tell me what's wrong with this test. It's the one that was set only this summer. What is wrong? Oh, well, the class yesterday were quicker, I think, on coming up with the answer. Anyone want to shout? That is going to be involved in the answer, actually, water vapour. You know, one of the things that I said before is, you know, don't call that a greenhouse gas. And that really contributes to the natural baseline greenhouse effect. No, well, so you're on the right track, but really what is the essence of this question is, and it may well be written in the curriculum, you may read it, but it's wrong. It's not the greenhouse effect, it's the enhanced greenhouse effect that is the issue here. So if it was the enhanced greenhouse effect, then I think you pretty much would say carbon dioxide. If you're going to say the greenhouse effect, well, you might say water vapor, but then you'd be wrong because it's not a gas. So you have to think about that this was a not a brilliant question. Yesterday I called it an awful question, and that the NUI examiner ought to be shot. I haven't changed my opinion much in the last 24 hours. So, the things that John and I have talked about, as he said, we do have an education section on our CRAC webpage, web links, podcasts. There's even some ebook samples for something that's available on the Amazon site by myself and an artist on ozone depletion and greenhouse effect. Our website is at the bottom, and I'll just finish on the immortal words of Ben and Jerry, Save Our Swirl. Okay, thank you.